Non vediamo che sta registrando. Adesso sì.
Now yes, but I swear that I clicked that button.
Ok, ok, grazie.
Thank you for reminding. So even if I had good intentions, I wasn't able to start the recording. So here we are. We have seen the other big problem, the thermal problem, so the survivability in very different thermal environments, from the thermal environment of Venus to the cold environment of Saturn. And essentially all science instruments couldn't work till Jupiter. I have said nothing so far on, or almost nothing on the cruise phase, but probably yesterday I said something. Let me grab the laser pointer. We said something about the trajectory. And we said something about the Saturn orbit insertion maneuver, which was quite delicate because the spacecraft had to pass. Let me see if, okay, here, this is the incoming trajectory, had to pass through the rings in a gap in the rings of Saturn. And you know, there are good information, a priori information about the possibility of the amount of dust and particles in these gaps. And these are obtained mostly by means of radio occultations. Okay? So we were relatively sure that the risk was small. The things would have been completely different passing through the rings, where there are boulders which are 10 meters made up of ice, 10 meters size, in addition to smaller particles. So navigation had to be precise, but let us say that so there is a requirement on the orbital accuracy to make all these maneuvers. But it wasn't a big problem. In any case, during the Saturn orbit insertion maneuver, the high gain antenna was pointed in the RAM direction, which luckily coincided also with the direction, the velocity direction, which luckily coincided also with the direction of the thrust that was applied. So the antenna acted also as a shield against possible collision with small particles. And I have to tell you something interesting about this, because the thermo-optical coefficients of the high gain antenna were known in the cruise phase. They were measured at launch, alpha and epsilon had a given value. Then they changed, increased significantly, varied also by a factor of 3 due to the outgassing of the polar molecules trapped in the paint of the antenna. And then it stabilized. After Saturn orbit insertion maneuver, those thermo-optical coefficients, especially the absorbance, changed by a significant amount, not big, but significant, as if the surface of the antenna was somehow cleaned up or stained, let us say, by the dust particles in the rings. Because even if there are gaps, these gaps are not free from particles. The density is small. They resemble more or less to the size of particles, solid particles of smoke, but they did an effect. They had an effect. So with the half of its mass, Cassini started its tour of the Saturnian system, encountering many times the various satellites. I won't say much about Juno, which is another interplanetary, we can skip, is another example of an orbital spacecraft, in this case of Juno. I have also an instrument on board. I had an instrument on board Cassini, and I had an instrument, I have an instrument on board Juno, which is currently orbiting Jupiter. So let us keep it all the way. But before skipping, let us see how different the design of this spacecraft is with respect to Cassini. First of all, power is provided by solar panels. So it was a choice of the project to use solar panels and not RTGs. Why? Because they are much cheaper. And for reaching the scientific goals of the mission, solar panels, the power required was enough. Also because the orbit, differently from the case of Cassini, the orbit of the spacecraft, let me see if I have a picture of the orbit. No, which is a pity, but essentially, okay, here it is. You see, the orbit is a highly eccentric orbit with a perigee just above the cloud tops of the planet, 3,000 kilometers above the cloud tops. So Juno had repeated encounters. Here the orbit is almost parabolic. Okay, repeated encounter of the planet. And is stuck essentially in this orbit were not for gravitational perturbations due mostly to the J2 of the planet. So, for example, the line of axis precesses and goes from this direction, from this orientation to this orientation after a number of years. One of the problems that one has with the spacecraft powered with solar panel is that you have to avoid eclipses. Jupiter is big, and when you are into eclipses, of course, you need to have enough energy storage on board. You need to have batteries, and you have to shut down all non-essential, all the payload, all non-essential instruments are shut down, etc. And the spacecraft must survive eclipses. Also, the thermal condition of the spacecraft changes because it's no longer sunlit. Okay? So it's one important thing. The third simplification was to choose an attitude stabilization given by spin. So Jupiter is a spinner. The revolution, it revolves about its axis twice per minute or 3 times per minute. It depends on the mission phases. So it's a spinner, it's a spin stabilized spacecraft, which simplifies many things, but makes also remote sensing observations quite complicated. And I wanted to show the difference in the design of Cassini and Juno. Juno is a much simpler spacecraft, much simpler. But it has to face a big problem which worried the mission designer. And the problem is, you see it here, is due to the radiation belts of Jupiter. Jupiter has a magnetosphere, which is far more extended and intense than the one of the Earth. The magnetic field of Jupiter reaches on the surface, the highest value is about 7-8 Gauss against the 0.3, 0.6 Gauss on the Earth. So around Jupiter there are huge radiation belts. The radiation belts are mainly mid-latitudes and equatorial. So with a polar orbit like this, actually Juno spent relatively limited time inside the magnetosphere of the planet. And therefore was less exposed to radiation. Nonetheless, all critical instrumentation, due to the presence of these radiation belts, had to be put in a vault. The vault, in Italian, literally sarcofago, okay, or volta, is a space inside the spacecraft which is protected by thick aluminum walls to reduce the amount of radiation that passes inside. So all the essential instruments, telecommunication system, transponders, computers, power controller, etc., were located inside this space, which was quite large, about 1.5 cubic meters, that was inside the spacecraft. And everything was inside this vault protected. One of the problems of the exploration of the Jovian system, especially the moon Europa, which hosts a subsurface ocean, is that if you want to put an orbiter around this satellite, Europa, very interesting from the point of view of exobiology, well, essentially even a radared electronic components cannot survive for longer than 3 months, 3-4 months, even if protected by a thick shield of aluminum. Okay, so radiation is a driver to the mission design, and protection against radiation is a driver on the mission design. And there are a number of requirements. The system engineer has to take into account the requirements posed by the environment. I wanted to say only this on Juno, how the orbit is partitioned, etc. But I don't want to spend too much time. So we have treated in general the orbiters. They have many possible designs, and if you look at a spacecraft, every spacecraft is different from the other. And this tells us another important thing, that at least in planetary exploration, but in Earth observation as well, there is little room for standardization. So each piece is unique. Each spacecraft is different from the other spacecraft. You can reuse parts, but the assembly, how you put together the system, depends on, I mean, it's different from spacecraft to spacecraft. And this peculiarity, of course, has an important consequence, increasing costs. Because if you can't reuse a design, costs increase. There is little recurrence. In the aeronautical industry, the situation is completely different. Now, with the constellation of satellites, things are changing, because you have these constellations which, as long as they last, are made by a number of identical spacecraft. But even if you look at the GPS constellation, the satellite of the GPS constellation, has changed through time. Every generation, there are several generations of space satellites, and these satellites have a different design. Not terribly different, but have a different design. So let us move on in this broad overview of robotic exploration of the solar system. The next type of probe that we will describe are the landers. Landers are space probe designed to land and have a soft landing on a planet or a planetary body. And so far, we have landed on the moon, we have landed on Mars, we have landed on Venus. It's a long time. This was long ago, in the 70s, 74. The Russian, the Soviet, I should say, space program was extremely successful with Venus and was able to put 3 space probes able to transmit even images from the surface of the hellish, this hellish planet, because the temperature was about 450 degrees Celsius. So they won't survive for long, 1 hour, the longest, but we got images also from the surface of Venus. Then we landed on Titan. Okay, we will see in a moment the Huygens atmospheric probe. We landed on Titan, a moon of Saturn. We landed, although not very successfully, on the comet Churyumov-Gerasimenko, the comet, the Rosetta comet, and the lander Philae. It was not a really successful a successful landing, but we landed also on the comet. We landed on asteroids, the asteroid Ikotawa by a Japanese probe, and also today we have a mission, a NASA mission, OSIRIS-REx, which is orbiting Bennu and will bring back some samples from this asteroid. So there is a number of bodies in the solar system where we landed. And the landers are quite different depending on where you have to land. What you see here is a sketch of what was probably the first extraordinarily successful landing mission, the Viking 1 and 2, the Viking mission, made up by two nearly identical landers. They landed on Mars, let me see, but I don't have anything but this sketch. And the landing was made by, let me grab the laser, the laser pointer I have already. Here you have a descent engine. So landing on Mars was made easy by the atmosphere. So there were initially also parachutes that were used, and heat shield for the entry phase. And then finally, the final phase was done with this terminal descent engine, and stabilization was provided by thruster. So Viking landed successfully on the planet with its set of instruments from cameras, meteorological sensors, etc., etc. It discovered the big dust storms on Mars. Other thing to say, telecommunication to Earth were provided by a relatively small high-gain antennas. Also this is a parabola, you see, also this one is a parabola. And I don't see here the RTGs here RTGs. They are inside the wing cover. Okay, so power was again provided by RTGs. And we had the first beautiful images of the red planet from Viking 1 and Viking 2. We were in 76. So they were launched in 76, landing shock absorber, and so on. Then Mars exploration, the next step are rovers. Rovers have the capability to move on the surface of the planet. But before I talk about rover, I would like to go back and discuss with you and compare the difficulty of landing on a satellite like the Moon and landing on Mars or Venus. Also Mercury, landing on Mercury was conceived. And what do you think? Is more complex, easier to land on the Moon or to land on Mars? What do you think from the engineering point of view?
Mars.
Why Mars?
Because of the atmosphere.
So your colleague answered Mars because of the atmosphere. I would take the opposite view, that the atmosphere helps. And the reason is that if you want to land on an atmosphere-less body, you have to carry a lot more propellant. because all the deceleration and everything has to be done with something that you carry on board, propellant, engines, etc. On Mars, you have seen the beautiful, and if you didn't yet, I suggest to see the beautiful movies of the landing of Perseverance, with the parachute, the heat shield, and so on and so forth. So the atmospheres makes the system a little bit more complex, certainly, because you need a parachute, you need a heat shield. But most of the delta V required to land on the surface is provided by the atmosphere. So you have to protect yourself, sure, but you need not to carry with you a lot of propellant. The moon is relatively easy because it has a low gravity. It's a low density, a relatively low density body. So the gravity is also, it's not large, it's about 1/10 the one on the Earth. But if you want to land on a very dense planet like Mercury, Mercury as a compressor is the densest body of the solar system, of the planets. So it has a fairly strong gravity field. And if you want to bring 1 kilogram of payload on the surface with a lander, you need 40 kilograms of propellant. This is the ratio. So it's much more difficult. While you can bring a large payload like a car, because Perseverance and MSL were as big as a 500, Fiat 500 more or less. Okay, mass more than 1 ton, and the atmosphere does everything. It would be prohibitive to use simply chemical propulsion to land. So you see, we had opposite point of view. Depends what is the meaning that we give to the word difficult, how difficult. Also, the question was a little bit ill-posed, my question, because in terms of complexity of the system, you need the parachute, the heat shield, etc. So it's a more complex system, but you may say, okay, landing on the moon is easier. It's just fire your engine, stabilization thruster, etc. Very easy, you go down. And in a sense, you were also right, because the system is simpler, but you can do a lot more with an atmosphere, with the aid of an atmosphere. Not to speak of the atmosphere of Venus, which is 90 times, actually even more, denser than the one of the Earth. The ground pressure is 90 times the one on the Earth. So they are a very small parachute does all the job. Okay. So this was the first rover, testing rover that was deployed on Mars. There were rovers, there was a lot of experience, NASA had a lot of experience, but also the Soviets, with rovers on the moon. Okay, also the astronauts used the rover on the moon. This was the first Martian rover. Very, very simple. Is a jewel of mechanics, small. Its dimension are less than a meter. Solar powered. Up here you have the antenna. It's a small antenna. The solar panels stay on top of the rover. So these are the solar panels. A posteriori, putting the solar panels there was a mistake because what happened? It worked for more than a month or a couple of months. And then at the first dust storm, the solar panels were covered with dust. And so their efficiency decreased significantly. And essentially the mission didn't last long for this reason. You don't have similar problem, of course, with RTGs. The next mission with the larger rovers was Mars Pathfinder, which brought on the surface two rovers with two separate launches, and it was really a beautiful mission. Let me see if I have. This is also a picture of the lander and the airbags together with the slide used by the rover to reach the surface. This is the slide. This is the airbag. And this is the rover. Okay. This is a mistake because the rover was not Sojourner, I think. Was not, no, sorry. I made a mistake. I said something incorrect. This this was the Mars Pathfinder mission, which brought the Sojourner rover on top of the surface of Mars. The mission was interesting. Why? Because NASA decided to use airbags. And so the airbags protected the probe, inflated at a certain altitude, and the spacecraft rolled inside these airbags. I have a movie of the Mars Exploration Rover later that we can see. And this makes landing extremely simpler. It can be used for small objects. Let me see if I'm able to. Oh, now it's time. It's time for the break. And so we stop here. And while during the break, I will try to have this movie going. Okay? So we stop here and we reconvene at 1:20. Okay, we reconvene at 1:20.
Professore,
Sì?
potrebbe ridire la parte perché è più difficile atterrare su Mercurio che la connessione mi saltava?
Why is more difficult to land on Mercury? Simply because Mercury has a much stronger gravity field than the Moon. And so, in order to land on Mercury, you have to first enter in orbit, and the orbital speed is larger because gravity is larger. And then you have to stop and start the descent in a strong gravity field. So the propellant that is required to arrive at a reasonable velocity on the surface is larger. Clear?
Sì, sì, grazie.
Okay. So let me see if I can, if it works when I do screen sharing. Okay, it works. Do you see it on the screen? Yes, perfect. We start with FBI warning. Allora, il corso adesso noi abbiamo iniziato con una parte discorsiva, ma insomma, non continua perché appena cominciamo la parte di determinazione orbitale, invece cambieremo una parte decisamente anche più matematica, più quantitativa. No, noi stiamo facendo semplicemente un overview perché mi è stato chiesto giustamente di fare un overview generale delle missioni scientifiche sul payload, sui differenti requisiti e così via. Quindi cerchiamo non la facevo questa parte. Quest'anno ho deciso di rifarla e comunque ecco, tra oggi e lunedì finiamo. E poi cominciamo invece con la parte di determinazione orbitale. C'è una missione che da Mercurio, poi di Colombo, non so se vi avevo parlato, l'ambiente spaziale. Adesso in marzo abbiamo il primo esperimento di congiunzione solare, che è il primo test di relatività generale. Solo che, ecco, sono problemi interessantissimi anche dal punto di vista così di come spremere al massimo quello che la sonda spaziale può dare. Ed è istruttivo anche per mostrare come i requisiti che noi diamo, no, magari molti anni prima, poi alla fine, quando si va ad usare il sistema, questi requisiti non sono rispettati. Per esempio noi abbiamo chiesto un periodo libero da manovre durante la fase di crociera di almeno 15 giorni, da manovre di desaturazione delle ruote. Le ruote servono per controllare l'assetto, no? Adesso vedremo, noi diciamo una settimana sembra garantita, 2 settimane forse, se sono bravi, i pannelli solari a compensare le coppie, orientando, ci sono 2 pannelli solari sulle Colombo, se vengono orientati verso il Sole con una differenza di mezzo grado l'uno dall'altro, non si sa bene quanto, allora si contrasta una coppia di pressione di radiazione solare che fa partire una manovra di desaturazione delle volte automatica. Quindi questo è un problema importantissimo. Vedremo. Intorno all'occhio. Speriamo che quelli di Flying Dynamics, che sono bravi, no? Ci aiutano moltissimo, però anche loro dicono che la prima volta che lo facciamo bisogna vedere come vanno. Certo, se alla prossima congiunzione ne sapremo molto di più. Come rispondono a questo, perché voi avete questo sistema, due pannelli solari che servono per la produzione elettrica, e siccome questi sono leggermente disassati, stanno un pochino sopra il centro di massa, si crea una coppia, no, che tende a far ruotare tutto il sistema lungo questo asse. Questa coppia viene controbilanciata da una delle ruote. Però se si sbilancia leggermente il tutto, cioè se si piega un pannello un po' di più e un pannello un po' di meno, in realtà se questo è il piano orbitale, i pannelli sono messi per così, perpendicolarmente al piano orbitale, questa coppia si può contrastare abbastanza bene con i pannelli solari. Quindi vedremo.
Vabbè, la pressione solare la coppia.
Beh, la coppia principale, no? Siamo a 0,5 unità astronomiche già, e quindi insomma la questione di radiazione solare si fa sentire. Poi un'altra cosa della quale dovremo preoccuparci sono le fluttuazioni di radianza solare. Cioè il Sole emette un flusso di radiazione che varia su scale temporali che vanno dall'ora alle 6 ore, anche il giorno, dall'1 per 1000 all'1 per 10.000. Quindi la costante solare non è veramente costante, perché ci sono macchie, dipende da quante macchie solari ci sono, dalle facole, cioè ci sono queste piccole variazioni. Queste piccole variazioni creano una variazione di radiazione solare che varia nel tempo. Quindi la sonda sente un rumore dinamico che vuol dire che è piccolo. Sì, è piccolo, ma i nostri strumenti sono sensibili, quindi noi lo vediamo molto bene. Se vogliamo fare una misura precisa, dobbiamo cercare in qualche modo di assorbire questi effetti. Quello che si fa generalmente quando il sistema dinamico non è soggetto a forze stocastiche, si usano modelli dinamici stocastici. Non credo che avremo tempo però quest'anno che avremo tempo di vederli.
Perché queste rotazioni sono imprevedibili, no?
Imprevedibili. Cioè da terra si possono misurare, perché ci sono dei satelliti e degli strumenti che misurano proprio l'irradianza solare. No? Misurano l'irradianza. Vogliono vedere quanto cambia, eccetera. Il problema è che, siccome siamo in congiunzione solare, perché vogliamo fare un test della relatività generale, quindi il fascio radio deve passare vicino al Sole e essere deflesso dalla gravità solare, allora il debito longo si va a trovare dall'altro lato del Sole, quindi non possiamo calibrare l'effetto. Perché noi vediamo la faccia del Sole, la nostra faccia del Sole, ma non abbiamo uno strumento dall'altra parte. Anche se i fisici solari mi dicono: guarda, non disperare, perché con misure di oscillazioni solari, misure su una faccia, è possibile con buona approssimazione sapere che cosa succede anche su un'altra faccia. Adesso infatti siamo in contatto con i fisici solari che insomma vediamo. Allora, bello poter, no?
Ma questa misura quali strumenti avete?
E sono gli strumenti di telemisure, quindi Doppler e range. Quindi una misura di range è una misura del tempo di volo di un segnale radio che va generato dalla stazione di terra, arriva alla sonda spaziale e ritorna indietro, quindi si misura il tempo di volo. E poi c'è anche uno spostamento Doppler associato a questo. E la gravità solare ha l'effetto, con un mezzo all'indice di rifrazione diverso da 1, ha l'effetto di provocare la deflessione, che forse voi tutti conoscete, ma ha anche l'effetto di, diciamo, cambiare il tempo di volo dei fotoni, perché lo spazio-tempo è curvo, ed è tanto più curvo quanto più vicino al Sole noi siamo. Quindi quando i fotoni passano vicino al Sole sentono maggiormente questo effetto, e il ritardo massimo che si può avere quando per un segnale che poi passa sfiora il Sole equivale a 72 km. Quindi è come se la distanza tra la stazione di terra e la sonda spaziale aumentasse di 72 km quando il raggio passa vicino al Sole. E 72 km sono tanti. No, se pensate che abbiamo un sistema radio che misura la distanza a livello di 2 centimetri, no, 72 km, li vediamo in realtà, passiamo un po' lontano, più lontano, sono 24 km equivalenti, però 2 centimetri, vediamo questi 24 km con una precisione di 2 centimetri, quindi è un ottimo test della relatività generale. Perché Einstein prevede 24 km. Però nessuno crede che la teoria della relatività generale sia la teoria finale della verità. Anzi, sicuramente non lo è. Bisogna vedere a quale cifra decimale è elevata, no? Con 2 centimetri noi possiamo di precisione possiamo fare un test molto preciso. E siamo gli unici che fanno misure durante la crociera, praticamente. Sono gli unici esperimenti di crociera di Betty Balloon. Perché per come è costruito il satellite tutti gli altri strumenti non hanno visibilità praticamente, quindi è un esperimento abbastanza importante per la missione.
Ma a che distanza del Sole minima deve arrivare?
Il fascio radio arriva a 4 raggi solari. Quindi Betty Balloon si trova dall'altra parte del Sole rispetto alla Terra a 0,5 unità astronomiche. Il fascio radio arriva ad una distanza minima di 0,4 raggi solari. E noi pensiamo di poter fare la calibrazione del rumore del plasma della corona solare fino a 7 raggi solari, quindi tutta la parte da 7 a 4 in pratica è banda K. Solo il segnale in banda K sarà abbastanza immune dal plasma, ma anche quello molto perturbato. C'è tutto. Quanti di voi hanno fatto ambiente spaziale? Un numero abbastanza consistente, quindi voi sapete, no, la corona solare, avete visto, abbiamo mostrato anche i climati, no, è altamente variabile nel tempo, quindi insomma, questo crea un rumore elevato. Quindi noi lo combattiamo utilizzando più frequenze, un po' come si fa nel GPS, che si usano più frequenze. Ma la banda X entra, diciamo, il segnale in banda X è soggetto agli effetti di ottica fisica, per cui praticamente entra nel regime di cosiddetta scintillazione forte, in cui le variazioni di ampiezza del segnale sono dello stesso ordine dell'ampiezza, quindi ci sono periodi, per esempio, della durata anche di 20, 40, 100 millisecondi in cui il segnale va a zero, l'ampiezza del segnale va a zero, e viceversa periodi in cui raddoppia. proprio perché i vari fasci, le varie componenti del fascio alla stazione di terra si ricombinano in maniera costruttiva o distruttiva in fase. No? Se arrivano i segnali arrivano con la stessa fase, abbiamo un'interferenza costruttiva e abbiamo un'ampiezza doppia. Se arrivano con fasi opposte, il segnale è zero. Quindi, mentre la banda K è più immune a tutto questo. Vedremo. Adesso infatti c'è un science di pericolo. Io non potevo fare la presentazione, la fa il nostro collaboratore che sta preparando. Che sta lavorando su questo. Vedremo. Torniamo il 15 aprile, 15 maggio, quindi tra poco. Che ore sono? Scusate.
E 22.
Ah, 22, allora tempo di ricominciare. So we restart, okay? Can you hear me? We restart with a movie, so it will be a movie that describes the Mars Exploration Rover mission, which was something more elaborate. The rovers were much more elaborate than Sojourner, which was a small rover. Now let me find only, okay. Here, let's go. We start with FBI warning. I leave the music and I watch the movie.
SSC disconnect enable on. 35. Let guys go. Hydraulics go.
The launcher is a Delta rocket, so we have two Delta
Pressurized vehicle
rockets.
launch. Pressurized. SSC hydraulic pump control on. On. CLCDR. Pad B deck flush on. On.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, engine ignition, and liftoff of the Delta II rocket with the Mars Exploration Rover.
Program response is good.
Oops, sorry. I just wanted the laser pointer. So the after stage, this is the final stage. You can see the heat shield. Separation of the service module is separated before entry. This is the aerodynamic generator, then conveyor belts. It's realistic because I was at JPL when this happened and I saw the signal amplitude varying. It did several of these big bounces. This is an extremely clever system invented by a Soviet engineer, which allows to essentially, with the measurement of local gravity, to end up with one side, the important side, facing upward. Testing deployment of the solar panels. Then this is the camera, the antenna. You see the high gain antenna just deployed. Remember that you have to survive to 12 hours of night. One day on Mars is called a sol. So now the rover is configured to its final configuration. You can imagine there is a long checkout phase. The landscape is similar to the one that you find in certain parts of Utah. Now, during the night, all the instruments are stowed and is solar powered, remember. So essentially the rover is hibernated. From the mechanical point of view, it's a jewel because you can rotate on your axis. And there is a number of scientific instruments, especially for geology and geochemistry. One of the main goals was that it never went so fast. The maximum speed was 10 centimeters per second, but it went much slower. It never went this fast. So essentially 100 meters per day. It didn't have any autonomous navigation possibility. But it had a wealth of robotic systems on board. This is a microscope. You want first to clean up the weathering from the surface to have access to the texture of the rocks. And then the microscope in the end transmits images. Some geologists, of course, know very well how to interpret everything. Okay, how was the view from remote? Were you able to...
Sì, sì, si vedeva benissimo, professore.
Okay, very good, excellent. So we move to the next. So the next step was to send an even more complex rover, much bigger, and you can see how big it is. This rover is MSL, Mars Surface Laboratory, and it was really, from the engineering point of view, extremely complex. The landing was extremely complex because for such a large object, you cannot use airbags. It's too big. So you have to do a soft landing, and the mass, if I remember well, of this object is about 1 ton. So this is MSL in the clean room at JPL. Let me grab the laser pointer once more. Power now is plutonium, is given by RTGs. And the instrumentation is much more complex. You can see something definitely bigger than the previous rovers. But the systems are essentially the same. Okay, much more complex. You can see it here, all the elements. The camera, similar to the one that we have seen. A number of instrumentation for geochemistry, from alpha particle spectrometers and X-ray spectrometers. So when the solar wind or high energy particles impinge on the surface, they trigger the emission of X-rays and alpha particles, from which one can have information about the chemical composition of the rocks. There are the usual cameras and mostly instruments for geology. Okay. Here you have the high gain antenna, bigger than the other one, to transmit directly data to Earth. And the way in which landing occurred is something very, very, very tricky. Why? Because the first part is essentially the same as in the case of the Mars exploration rover. So you have a service module, a heat shield. You separate the service module, the so-called cruise stage separation. The service module is abandoned, and you start entering. You have a deceleration. Mars has an atmosphere which on the surface is about 100th in terms of density, the one of the Earth. So the decelerator does most of the job. You reach peak heating, peak deceleration, and then you are at hypersonic velocities, of course. And then at about Mach 1.5, about Mach 1.5, you deploy the parachute. The velocity slows down in a quite significant way, and then at that point you can get rid of the heat shield, which you'll see here. So the heat shield goes away, and then the sky crane comes into play. The sky crane is a very complex system that you see depicted here. Let me, I don't know why you are seeing here I don't see the image of the participants on this screen. I don't know why they are there. Anyway, what happens is that at a certain altitude, laser pointer, come here. Okay, here the power descent starts. So what happens is that you have a module with a propulsion system, which is up here. And then the rover is deployed on tethers down at about 50 meters away. You see it here. So you have the so-called sky crane. So this module hosts thrusters, and the module hovers over the surface of the planet while releasing the rover. The rover is down here. Okay? So gently, by means of a radar altimeter, very gently, the sky crane deposits the lander on the surface. Time is entry plus essentially 416 seconds. So everything happens extremely quickly, has to be done automatically. So there is no possibility to control the descent from Earth. And then the tether is severed and the sky crane is thrown away in order not to crash on the rover. Okay? So very complex system. And I would say probably the most complex system that NASA has ever built, at least in terms of planetary exploration. So it was successful, and it was reused, the same concept for Perseverance. What can we say? Again, here, a lot of help was provided by the atmosphere of Mars. Without an atmosphere, such a mission would not be possible at all. Okay, simply because we had not the capability to carry enough propellant to do that. And the human mission to Mars, if we want to think to that, probably will be much bigger, much more expensive. So at that point, this was a $2 billion mission, but a human mission to Mars, we are in the order of $50, $60 billion at least, if not 100. So in that case, probably we can carry the propellant to do a controlled descent without the need to use things like sky cranes or similar things, which pose additional risks. because the more complex a system is, the riskier the things are. So this is how MSL and Perseverance went down. Now let us change to a different class of missions, the atmospheric probes. And one probably the most famous of them is the Huygens atmospheric probe, which sampled the surface of Titan. The concept is very similar to the one that we have seen on Mars, with the advantage that Titan has an atmosphere with a density similar to the one of the density of the Earth atmosphere. Pressure on ground is 1.4 the pressure on Earth. The atmosphere is denser than the one on the Earth, but the concept of entry is essentially the same. We have a heat shield. The probe is inside here. At Mach 1.5, a parachute is deployed. First a drogue chute, then we have the main chute deployed, and then the descent lasts about 2 hours. And the parachute was designed in order for the descent to last a long time, because the main goal of the mission was to gather information on the structure of the atmosphere of Titan. So you don't want a fast descent, not for 100 seconds. You want to stay there for 2 hours. And during the descent, a number of atmospheric parameters, measurements were done. Also a camera was used to look at the landscape of Titan from below the clouds. Because here the clouds that prevent any observation, at least in the optical band, from outside. And the images were quite astonishing. I have a movie also of the descent of the camera, but we don't have time to see it now. So the concept is essentially the same. And atmospheric probes are probes whose the mission lasts only a couple of hours, with a very specific goal. If you want to stay for longer in an atmosphere, what could you use? For example, at Titan or at Venus. You can use aerostats, balloons, okay? Montgolfiere. And believe it or not, they were used by the Soviets in the early 80s. The Vega balloons. The Soviets deployed 2 balloons at Venus that lasted for more than 4 months. There was little control of the altitude, although in principle you can also control the altitude. Okay. But if you want to stay for longer in an atmosphere and do in situ measurements, a balloon is the way to go, at least at high altitudes. If you want to stay at low altitudes, but these are not atmospheric probe, you can use drones or quadcopters, octopters, and similar things that we will see in a moment. Huygens was not designed to survive the impact with the ground on Titan, but it did survive. It did survive and transmitted images from the surface for about, and also data from the surface for about 2 hours. In this case, communication was not direct to Earth, because this atmospheric probe has had no attitude stabilization, not at all. Was spinning during the descent. It would be too complicated to have attitude control. So it landed and survived the landing. Power was on batteries. When the batteries were over, game over. It lasted for about 2 hours. The cost of the Huygens probe was not large. If there was a requirement to guarantee survivability of the probe on the surface, the costs would have probably at least doubled. Because if the scientists required survival on the surface for 2 hours, the engineers automatically have to guarantee the survivability to the impacts. So stronger structure, perhaps also some engine to decelerate the last phase, the last few meters of the descent, and so on and so forth. But engineers were reasonably confident that the system would have been able to survive. Another class of mission which was very fashionable and sometimes were penetrators. These are simple things. So you essentially do a hard landing on the surface, little control, acceleration 800G, 200G. So essentially you drop a small probe on the surface, and as in this case, the penetrator is made up by a part which, due to its kinetic energy, penetrates in the soil. You can imagine that the scientific payload is really modest, very modest. And in fact, penetrators now are completely out of fashion. I mention them only to see that you can do something also in this way. More interesting is the concept that has been pursued by NASA, and the concept in this case is a rotorcraft. And here you see the one here is the Dragonfly rotorcraft, which is an 8 blade. It has eight blades, 2 and 2, so 4. So it's an octopter. Okay, not a quadcopter, octopter. And the target is Titan. So Dragonfly, which will be launched in 2027, was selected 2 or 3 years ago, launched in 2027, powered by RTG. Here you have an RTG, which is used to recharge the batteries which are inside the body of the Dragonfly. And the interesting thing is that Dragonfly will be deployed with a standard system similar to the one that we have seen for the Huygens probe. But then it has the capability to fly to a significant altitude, 1,000 meters, above the surface, and on a range of about 8 kilometers. The range is determined by the energy stored in the batteries. So the mission profile, you can see it here, that's the parameters. The landing mass is large, 450 kilograms. Okay? Power is 70 watts from RTGs. So there is the classical landing, and you can see here a number of parameters. But how does Dragonfly operate? So Dragonfly lands. Then once the batteries are charged, fully charged, it does a first flight, okay, in a given direction, with the cameras pointing down and looking at the flight path, and at the surface below it, and at a certain point it arrives on the target landing site, takes images of the landing site, and comes back to the original location. The original location is a safe location, a location where the rotorcraft can land without problems. The putative landing site could be very rough. We don't know. Okay, we don't have enough resolution to see to tell whether is a place suitable for landing. It's not like Mars. We have high resolution images of Mars, plenty of them. So we can identify very easily areas where landing is easy or not. But on Titan, we don't have this luxury. So there is this trip, two-way. Then the images are analyzed, transmitted to ground, analyzed by geologists and engineers, and they decide whether the landing site of the next flight is suitable, or if it's better to land in a different location, nearby location. So Dragonfly is programmed to fly to that location, and you do a first flight. In flight, you do a number of science measurements. The payload is not terribly rich, but it will provide important information on the chemical composition of the soil, etc., and a number of things. So from the point of view of robotic exploration, Dragonfly is really a breakthrough. Unfortunately, Titan is far away, and launch is 2027, arrival on Titan is in 2038, if I remember well. Here is not mission duration, 12 years, 2.7, 37, not 38. Okay? So one need to is a really exciting mission. I know I have many of my friends who are who essentially conceived this mission, but you have to be extremely patient. And in 2037, they will be all retired, I will tell you. Okay, so one has to be extremely patient. Different is the story of Ingenuity, which is a much simpler rotorcraft, which is brought together with Perseverance. I know also the group who designed it. Mimi Aung, a friend of mine, is a program manager, project manager of the mission. And I think it's March, when is, just before the end of March will be the first test flight. It's much, very different. This is, has two blades, which are large, 1.2 meters, if I don't remember. Oh, yes, the rotors are 1.2 meter wingspan, and the mass is very, very small. It's like one of our drones. Total mass is 1.8 kilograms. Okay, the battery is 270 grams. Power, more power than in the other case. Why? Because the atmosphere of Mars is much thinner than the atmosphere of Titan. On Titan, you have the density, the atmospheric density is large. So you can survive with smaller wings. And you have two rotors here rotating in different, in opposite direction for stabilization. And you have also a solar panel up here. So charging is provided by a solar panel. The flight altitude is about 5 meters, so not much. Is a test, we can consider it okay, a technology demonstration mission, in a sense. So a totally different story, but we will see. It's, the concept is very interesting. It will test also cameras and to a certain extent use artificial intelligence for these flights. However, the flights are short, very short. I don't remember, 100 meters probably. I don't remember if it's written here, but not more than the range is a few hundred meters, because you have to keep contact with Perseverance. So, okay, here are additional, yes, maximum range 50 meters. For radio, 1 kilometer. So you have an idea of, well, the rotor speed is quite significant because it's 2400 RPMs. This is again Dragonfly, additional information. And however, let me, before we start a few considerations about system engineering. We will start on Monday. In this 30 seconds, I would like to tell you that there are also other type of probes that are conceived for robotic exploration of the solar system. And one are, let us say, boats. There is a body, Titan, which has a large hydrocarbon seas. And so there is a mission, or I mean, which includes also a boat. And the second thing, very interesting, is a submarine. A submarine to be used on Enceladus or Europa. And we will say just a few things next time. We will spend 5 minutes about these two classes of probes that you may be able to see in your career. Okay, we quit here. So I stop sharing. I need the pen.
Professore, una domanda.
Oh, please.
Sì, io ho notato che le pale dell'Ingenuity sono in fibra
Just
di
a moment,
carbonio.
excuse me, I
Sì.
turn on the volume. Please go on.
Dico, ho notato che le pale dell'Ingenuity sono in fibra di carbonio, ma essendo comunque sia la resina sia la fibra di carbonio soggetti molto alle radiazioni, in particolare quelle solari, come è stata gestita questa cosa?
So the question is, the blades are in carbon fiber, which are very sensitive to solar radiation. Well, it's very easy because at Mars, Ingenuity will do, I think, 2, 3, maximum 4 flights. And then it will be discarded. So it's not a problem for such a short time span. Okay?
Capito, grazie mille.
On Dragonfly, I don't remember. Do you remember what is the material of the blades? But in that
Non penso
case,
che l'abbiano specificato ancora.
yes, but in that case, you see, solar radiation is not a problem because first is 110, 100, the intensity is 100, the one on the Earth. Second, there are these very thick clouds, and so solar radiation, the intensity of solar radiation is really small.
Sì,
Okay.
capito. Grazie mille, buona giornata.
Arrivederci. Other questions? Okay, so thank you all. I stop recording, stop sharing.